Hello everyone. So today I have a really fun problem for you involving solving equations in algebra. It's an AMC 12 problem, and we're also going to see how the options given on the AMC exam make our life a lot more simpler. So let's begin. And like I said, this is an AMC 12A problem. It's in fact the problem number 13 from the AMC 12A conducted in 2020. And in this video, we're going to see a problem that can be transformed into a solvable equation. And we're going to see how, most importantly, we're going to see how to use the options on the AMC to advantage. So because we have those 5 options given in the exam, we can use them and somehow make our life simpler instead of going for those number theoretic approaches, right? Then we're going to look at certain book suggestions for the AMC, and at the end we have a similar and challenging problem.
This video is sponsored by Cheenta.com. Since 2010, Cheenta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students. Cheenta programs are designed for students who are passionate about mathematics, and they are personalized with one-on-one training, individual evaluation, and remedial sessions.
So let's see what's given to us. We have 3 integers a, b, and c. Each of them is greater than 1, so that they satisfy the given equation with n not equal to 1. And then we need to find out the value of b, right? And this is the equation given. Now we have some radicals over here, so let's just try and simplify the left-hand side and see what we can get. So I can write this as the 8th root of n times the bth root of n times n raised to the power 1 by c, right? And this can be further written as the 8th root of n times n raised to the power 1 by b times n raised to the power 1 by bc, which can simply be written as n raised to the power 1 by a times n raised to the power 1 by ab times n raised to the power 1 by abc. And using laws of exponents, we can write this as n raised to the power 1 by a plus 1 by ab plus 1 by abc. This is just standard rule of indices that you must have studied. And on the right hand side, we have n raised to the power 25 by 36. So the bases are same. We can equate the powers, which basically means 1 by a plus 1 by ab plus 1 by abc is equal to 25 by 36. Now, believe it or not, this is an equation that we can work with, right? This is not a bad result. And if I just take abc in the denominator and I just kind of rewrite this, I will get bc plus c plus 1 is equal to 25 by 36. Now after this, if I write without loss of generality, if I consider abc to be equal to 36, which is 2 square times 3 square, and if I just consider bc plus c plus 1 to be equal to 25, or in other words, c times b plus 1 to be equal to 24, which is 2 cubed times 3, 8 times 3, this is what we get, right? So let me just rewrite this. abc becomes 2 square times 3 square, and c times b plus 1 becomes 2 cubed times 3, right? 8 times 3 and 9 times 4. Perfect. Now we can see that a, b, and c will be of the form 2 raised to the power x times 3 raised to the power y, right? Where x and y are greater than or equal to 0. That's pretty obvious over here. Now another thing that we can see is b plus 1 is a factor of this, is a factor of 24. And b, that is one number less than that, is a factor of 36, right? So b plus 1, basically b plus 1 divides 24, and b, which is one number less than that, divides 36, right? It's a correct statement if I say that. So if we can just somehow maybe get the value of b, that would be great, right? So it probably won't be a bad guess to check for the case if b is equal to 3. Right? If b is equal to 3, then b plus 1 is equal to 4. And then c turns out to be 6. Right? If c is 6, b is 3, then that gives us a is equal to 2. Right? From these two equations. So this 2, 3, 6 is actually a valid pair that satisfies the given equations. Right? And 3 is there in the options as well. So we kind of know that 3 is the correct answer. But we got to this without even seeing the options, and I had said earlier in the video that we can use the option to our advantage, right? So instead of this guessing, instead of this estimation that b will be 3, using the idea that b plus 1 divides 24 and b divides 36, we can just directly check the options. right? We have this equation, c times b plus 1 is equal to 24, right? If I take any of these options, I'll show them for one of you. For instance, if I take the option D, right? If I take b is equal to 5, if b is equal to 5, then this will be 6, so c will be equal to 4. But then ABC has to be 36, so 20 times a has to be 36. That means a is equal to 36 by 20, which is not an integer. Therefore, we need to reject this. Similarly, you can see for the other options as well. None of these options satisfy other than the second option. So in options A, C, D, and E, in all of these 4 options, you'll realize that one of ABC, one or more of ABC, will be non-integral, which means that they won't be integers. And that is why just by the process of elimination of options, we can actually solve this question. So the key idea is, once you reach till this step, it's important to reach till this step, but once you've reached till that step, after that you can just use optional elimination. You can just plug in the values of b and check if it satisfies or not. And once you have these 2 simultaneous equations, you can actually see that b is equal to 3 actually satisfies, and that is the correct answer. So I hope you like that. Right, so we have certain book suggestions for the AMC. We have Mathematics Can Be Fun by Yakov Perelman, Mathematical Circles, the Russian Experiment. Then we have Algebra Can Be Fun by Yakov Perelman. Then we have Excursion Mathematics and the very famous Challenges and Hills of Pre-College Mathematics. So now at the end, we have a similar but challenging problem for you. And this involves a little bit of the greatest integer function, also called as the floor function. And they have given us, let any real number t, let the floor of t denote the largest integer less than or equal to t. They basically just define the greatest integer function, right? Greatest integer function, this. Now suppose that n is an integer that satisfies the given equation. Find the sum of digits of n. So for those who don't know the greatest integer function, let me just kind of explain it in brief. So the greatest integer function of 2.3 will be 2, right? What does that mean? It means that what this function does is it tells us the greatest integer less than or equal to x, right? So the greatest integer of x, the greatest integer function, it tells us the greatest integer less than or equal to x, right? What is the greatest integer less than or equal to 2.3? It is 2. What is the greatest integer less than or equal to 3.9? It is 3. It needs to be less than that number, right? It is not rounding off, okay? What is the greatest integer less than or equal to 4.5? That will be 4, right? What is the greatest integer less than or equal to 5? That will be 5, right? Greatest integer of x is x if x is an integer, right? Similarly, the greatest integer of negative 3.7 is negative 4. And really, we can see that using a number line. So we will have negative 1, negative 2, negative 3, negative 3.7 will be somewhere here, and then we will have negative 4 over here. So if I had written negative 3 would actually be greater than negative 3.7, and that breaks the definition of the greatest integer function. So therefore it would be negative 4. And just like positive integer, greatest integer function negative 3 is negative 3 indeed. So that was kind of the idea of the greatest integer function, and now that you have that idea, you can try and try solving this question, and if you make any progress on it, please do let me know. Alright, until then, I'll see you in the next video. Bye bye.
The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit cheenta.com.